In this lecture, we will discuss about moment generating function. So this is very important concept or very important topic. Moment generating function. In short, we write MGF, moment generating function, which generate the moments. So now we define this moment generating function. So we write down as the moment generating function. In short, we know that the MGF of a random variable x. So this random variable x we consider at the origin. So about origin, we can also calculate for any value, that means about x equal to a. So first here we define for origin, having the probability function fx, which is given as mxt. So moment genetic function we defined as mxt. Mxt is equal to expectation of e raised to the power tx. So mxt we can define as expectation of e raised to the power tx. This equal to, so we can define in two ways. One for कंटिन्यूस प्रोबेबिलिटी डिस्ट्रीब्यूशन, सेकंड फॉर डिस्क्रीट प्रोबेबिलिटी डिस्ट्रीब्यूशन. तो आप जानते हैं जब कंटिन्यूस प्रोबेबिलिटी डिस्ट्रीब्यूशन यूज करें, वी हैव द इंटरवल, सो वी यूज द इंटीग्रेशन. तो इंटीग्रेशन, so we write down as e raised to the power tx into fx dx. So fx dx, that means we do the integration. So this is for continuous probability distribution. So this is for continuous probability distribution. So we write down for discrete probability distribution. So in discrete case, we use the summation. So summation we write down e raised to the power tx into px. So px means probability mass function, or fx we write down for the probability density function. So this is for discrete probability distribution. So this is for discrete probability distribution. So we explain this moment genetic function. So that means that generate the movements. So now we write down this as mxt. So here we take a t be the real parameter. So we write down this as t be the real parameter. So t is the real parameter, and x also the real parameter. Okay. So we write down as mxt. So this mxt we can have written as expectation of e raised to the power tx. Now, when we expand this e raised to the power tx, so what is the expansion of this? So we know that the expansion of e raised to the power x, expansion of e raised to the power x is 1 plus x square upon factorial 2 plus x cube upon factorial 3 plus and so on. So this can be proved by using the Maclaurin theorem. So with the help of Maclaurin theorem, we can expand this Maclaurin theorem. So now when we expand this, so similar we use the uh, expansion of this. So we write down e raised to the power t. So what is the expansion of this? So the expansion of this is 1 plus tx plus t square x square upon factorial 2 plus tq xq upon factorial 3 plus t raised to the power 4 x raised to the power 4 upon factorial 4 plus and so on. So the next term we can write down as t raised to the power r x raised to the power r upon factorial r plus and so on. So we expand this now. We know the properties of expectation. So general properties we have already discussed it. So the properties we have discussed here also. So expectation of Cx, C means constant. So this can be written as C into expectation of X. Now we can write down as expectation of Ax plus By. So this can be written as A into expectation of X plus B into expectation of Y. Okay. So when we have a simple two random variable X and Y, so this can be written as expectation of X into X plus expectation of Y. So similar, we use the properties of expectation here. So we write down as expectation of 1 plus expectation of tx plus expectation of t square x square upon factorial 2 plus expectation of tq xq upon factorial 3 plus and so on. Or next we write down as expectation of t raised to the power r x raised to the power r upon factorial r plus and so on. So when we take the expectation of any constant term, this gives us constant. So means expectation of 1 is 1. Expectation of 1 is 1 plus of t be the parameter. So t be the parameter, x be the random variable. So we can write down this as t, treat as a constant, means cx. So one property we have written this one. So we use this property. So we can write down the t into expectation of x plus next term you can write down a t square upon factorial to treat it as constant c. So this can be written as expectation of x square. अगला टर्म क्या लिख सकते हैं टी क्यू अपॉन फैक्टोरियल 3 इंटू एक्सपेक्टेशन ऑफ एक्स क्यू प्लस एंड सो ऑन प्लस नेक्स्ट टर्म विल बी t raised to the power r upon factorial r into expectation of x raised to the power r. So we can say that this expectation of x we represented as the mean. So we can write down this as so we x e raised to the power x e raised to the power x square x q x raised to the power r we consider as the mu1 dash mu2 dash mu3 dash. So this we consider as mu1 dash. So this e raised to the power x square we consider mu2 dash plus tq upon factorial 3. This we have written as mu3 dash plus and so on plus t raised to the power r upon factorial r into mu r dash plus and so on. So now when we write this into the form of summation, so this can be written as r is equal to 0 to infinity. We write down as t raised to the power r upon factorial r into mu r dash. Okay. So this mu r dash, this mu r dash can be represented in the form. So mu r dash is equal to, we can write down as expectation of x raised to the power r. We already write on this place. So we have defined this as, so similarly we define for mu r dash when we have a continuous distribution. So we can calculate this as x raised to the power r into fx dx. So this is for continuous distribution. So we write down as for continuous distribution, or when we have discrete, so we write down as x raised to the power r into px. So this is for discrete. So this is for discrete distribution. दिस इज फॉर डिस्क्रीट डिस्ट्रीब्यूशन. आपको याद होगा जब हम एक्सपेक्टेशन डिफाइन करते हैं तो एक्सपेक्टेशन जब हम कैलकुलेट करते हैं एक्सपेक्टेशन ऑफ एक्स तो उसके लिए क्या फॉर्मूला यूज करते हैं हम. उसके लिए फॉर्मूला यूज करते हैं समेशन ऑफ एक्स आई इंटू पी आई. मीन्स वी डू द समेशन सो आई इक्वल टू we take as 1 to n. Now when we do the continuous case, so we take the integration of x into fx dx. So we do the integration for the same. So this is for discrete and this is for continuous. So similar thing we have written above. So now, so this mu r dash, so mu r dash is the rth moment. Which moment? Rth moment. Rth moment of random variable x about origin because we are solving about origin. So the coefficient of t raised to the power r upon factorial r, t raised to the power r upon factorial r in mxt. So this is our mxt, and the coefficient of t raised to the power r upon factorial r is mu r dash. So is mu r dash. So we write down as mxt gives mu r dash. So mu r dash about origin. So mu r dash about origin. So we can write down as so mxt क्योंकि ये जनरल टर्म है mu r dash. mxt generate the moments. mxt generate the moments. So it is known as moment generating function. Known as moment generating function. Moment generating function. Okay, so this mxt known as the moment generating function. Now, when we solve this one, so for solving this, so this is our general equation, main equation. We can consider this equation as 1. So now, differentiate equation 1 with respect to t r times. With respect to t r times by putting and by putting t is equal to 0. So after differentiation, we put t is equal to 0. So here we use the rth derivative. मीन्स आपको पता होगा जनरल केस हम कंसीडर करते हैं nth डेरिवेटिव के लिए. अगर y इज इक्वल टू फंक्शन है x रेज टू द पावर n. So we calculate the nth derivative means n time differentiation gives us factorial n. Suppose आपके पास कोई फंक्शन है y इक्वल टू एक्स क्यूब. So when we calculate y4 means fourth derivative because we have power 3. So on the third derivative this gives us the constant value. So fourth derivative will be 0. So similarly we can understand this when we are going to calculate our rth differentiation with respect to t. तो जो rth differentiation we calculate कर रहे हैं तो r से जो पहले वाले टर्म्स होंगे rth डेरिवेटिव से वो ऑब्वियसली जीरो हो जाएंगे उनके डेरिवेटिव्स. तो यहाँ तक जितने भी डेरिवेटिव्स होंगे इससे पहले इस टर्म से पहले rth डेरिवेटिव से पहले ऑल टर्म्स हैविंग डेरिवेटिव जीरो. सो दिस टर्म having the derivative, so we can write down as dr r time differentiation into d raised to the power r mxt. ये LHS साइड हो गई. अब इसमें डिफरेंशिएट कर रहे हैं विद रेस्पेक्ट टू टी और पुट कर रहे हैं उसके बाद t इक्वल टू 0. तो अब हम RHS साइड को देख रहे हैं तो ये तो डेरिवेटिव कर दिया हमने LHS साइड का. अब r का ये फर्स्ट टर्म ये जीरो कांस्टेंट है, सेकंड का भी जीरो हो जाएगा, थर्ड का भी जीरो हो जाएगा, फोर्थ भी जीरो हो जाएगा एंड सो ऑन. जब हम जनरल टर्म का डिफरेंशिएशन करेंगे तो टी की रेज टू द पावर क्या है, आर, और टी रेज टू द पावर आर का आर टाइम डिफरेंशिएशन क्या हो जाएगा, फैक्टोरियल आर, और डिनोमिनेटर में भी क्या है, फैक्टोरियल आर है, और इधर क्या है, म्यू आर डैश है, प्लस अब इससे जो अगला टर्म होगा, इससे अगला टर्म क्या होगा, टी रेज टू द पावर आर प्लस वन होगा, और अपॉन में क्या होगा, आर प्लस वन फैक्टोरियल। अब हम यहाँ पर कंसिडर करते हैं कि अगर हमारा y है, y हमारा हो जाए x रेज टू द पावर n प्लस वन, तो उसका जब हम y n डिफरेंशिएशन करेंगे तो क्या आएगा, n करेंगे तो n प्लस वन का फैक्टोरियल बनेगा, और इन टू में एक x बच जाएगा। तो सिमिलरली जब हम उस नेक्स्ट टर्म का आर टाइम डेरिवेटिव करेंगे तो वो क्या हो जाएगा, आर प्लस वन का फैक्टोरियल हो जाएगा, और अपॉन आर प्लस वन नीचे भी डिनोमिनेटर में भी फैक्टर होगा, और इन टू में क्या आ जाएगा, टी आ जाएगा, और इधर क्या हो जाएगा, म्यू आर प्लस वन डैश। ऐसे ही अगले टर्म्स भी आएंगे, तो हम एक ही टर्म को लिख रहे हैं। ये हमारा टर्म को लिखने का पर्पज क्या था, कि जब हम डेरिवेटिव कर रहे हैं, डेरिवेटिव के बाद हमें क्या करना है, पुट करना है टी इज इक्वल टू जीरो। तो मतलब जो आर म्यू आर डैश से जो अगले टर्म्स होंगे, वो सारे टर्म्स क्या करेंगे, टी कंटेन करेंगे, सारे टर्म्स टी कंटेन करेंगे। ये टी आ गया, अगले में टी स्क्वायर आएगा, उससे अगले में टी क्यू आएगा। तो जब हम टी इक्वल टू जीरो पुट कर देंगे, तो टी इक्वल टू जीरो पुट करने पे हमें क्या मिलेगा, केवल म्यू आर डैश रहेगा, बाकी सारे जीरो जाएंगे, क्योंकि पहले टर्म तो ऑलरेडी जीरो हो गए डिफरेंशिएशन में। तो ये क्या हो जाएगा, दिस गिव्स अस म्यू आर डैश। सो म्यू आर डैश, सो दिस मीन्स जो म्यू आर डैश की जो वैल्यू हो गई, दैट विल बी द डी रेज टू पावर आर अपॉन डी टी रेज टू द पावर आर इंटू mxt. So this is our movement generating function. So we remember this formula which generate the movement. अब इसकी help से we can calculate mu 1 dash, mu 2 dash, mu 3 dash. So we put as r equal to 1 2 3. Okay, so here we put r equal to 1 2 3 4. So calculating first movement, second movement, third movement, and so on. Okay, so you can calculate the movements. Now when we talk about the movement about any value, so suppose we are going to calculate moment genetic function about x is equal to a. So when we put x equal to a, first solve, we have solved for x equal to 0 origin. Now this we solve for x equal to a. So this can be written as expectation of e raised to the power t into x minus a. So when we expand this, so this can be written as e into 1 plus t into, again we use the expansion, plus t square upon factorial 2 into x minus a to the whole square plus t cube upon factorial 3 into x minus a raised to the power whole cube plus and so on. Next term will be plus t raised to the power r upon factorial r, or x minus a raised to the power r plus and so on. So this we can write down as 1 plus t into mu 1 dash plus t square upon factorial 2 into mu 2 dash plus and so on. So this mu r dash, so mu r dash means we write down as mu r dash. This mu r dash is equal to expectation of x minus a raised to the power r instead of x raised to the power r. In previous case, we have taken as e of x raised to the power r. So this is the rth moment. This is the rth moment about x is equal to a. So about x equal to a. So now we have various distributions. Suppose binomial distribution, Poisson distribution, normal distribution. So we can exponential distribution. So we can calculate the movement generating function of distributions and also calculate the mean variance related to that.